Yeah, you see it. It's
Oh, I know.
Basically the error marker. So basically we will allow that much choose and those or it's just the other way around.
So, how was Thursday? Was it good? Bad? We have the video. We didn't put it online yet. We will. We need to process it first. I hope you enjoyed the lecture. Professor Aslam was famous for his lectures. He doesn't teach, unfortunately, as much as he used to. So because he did something else that I was planning, then we have to talk about kNN neighbors, right? And to see a little bit of what we have left. This is the last week of classes. So, first things first, exam this Saturday, 4:20. And if you haven't done trace evaluations, please do so. And then this week, we need to deal with the project. There's few people who do projects, they might need to have a homework. Wednesday, Thursday are office hours this week. We have to see what that is. You don't have to finish necessarily by this Wednesday or Thursday. Do a project. You have to come talk to me Wednesday or Thursday and say, okay, here's what I have so far, here's what I plan to do. We still have about a week to finish that. And then I think the last homework due date is probably something like 24. Let's say maybe. I think it's that one, but let's see. Right? Okay. So what we have to do today is kNN's neighbors. I don't know yet. It's going to be, the reason we don't know yet is because there has to be a lot of power strips installed. It's very different in a laptop. It's not possible to draw power from the wall with like 50 people. So they have to figure it out. I believe it's WPH, one of the labs in the computer science building. And we are debating, me and the TAs, we're debating exam problems right now. Like how long is this going to take? It's interesting, but it's too long. That's so. Okay, so K. We already talked about what is this as an idea, and I'm sure you already know it, so I'm just going to recap that very quick. The basic idea of kNN neighbors is extremely simple. In fact, many machine learning classes, or even pre-classes, like what you have to know to start a machine learning class, is this. Like, here's a simple way to do stuff. So the idea here is that the prediction of Z is a test point. Prediction of Z is the label of closest point X in the training set. So if I want to know something about the patient, I say, what are the most similar patients with this one I'm seeing right now? If I know something about those similar ones, then I apply that same methodology to my current patient. Like if I apply a certain treatment that worked well, for example, then I know that and say, this patient is similar with that, I'll apply the same thing. Very basic idea. So how do we say this? We can define a neighborhood of Z, which are the set of, I'm going to write this in English first, close points X in the training set We still have a training set, but we're not actually training anything. To Z. So I have this neighborhood. So once I have this, depending on what my label is in nature, it could be a quantity or a category, I use this neighborhood as a final label. So if I have the prediction on Z might be the average label of that neighborhood. That's good for quantities. Quantities, Y. So that if what I'm predicting is a house price, for example, or a salary, something that's quantitative in nature, I can just take the average of prices in the neighborhood. It could be majority. So I'm going to write here average Y, if that's quantity. It would be a majority Y, that's a class. Or it could be some other heuristic. It could be a voting system. Consensus. In some problems, I don't want to predict majority. I'm only going to predict something. It's an absolute consensus in that neighborhood. If everybody in that neighborhood agrees that this is a sick patient, then I'm going to say sick. Otherwise, you know, like the juries, right, work like that. You've got to convince 12 people. Convincing 11 people is not enough, even though 11 out of 12 would be a strong majority. In juries, you got to convince all 12. So there are some problems for each. You may want to have absolute consensus that this is the case to make a prediction. So this is not that important, how you deal in the neighborhood. You know, once you have the neighborhood, how do I determine, you know, what prediction I need to make? So before we get into how to construct the neighborhood, which I think we mentioned briefly last time, that was a week ago, we have to go by a similarity function. I want to point out first, what is the difference between this local versus the other classifiers we dealt with in this class? So not all of them, but we talked about regression a lot, right? We talked about support vector machines, naive Bayes, on and on and on. So what can this do that the other ones don't? Yes?
It's not linear. It's not linear.
Right, it's not linear. Decision trees are not linear either.
But a lot of the other ones are.
So, but that's true. So this is not a linear classifier. In fact, it's robust, very robust in that sense. It's not just not linear. It doesn't make assumptions about the data form. Like you could say it's also not quadratic, because it doesn't make any assumption about how data looks like. But like as a visual, here's what I need to point out. Here's my point Z. That's the test point. Z, if I use a linear classifier like a regression or a support vector machine, will fall on some part of that classifier. It might be in the correct side or the incorrect side. But what determines this classifier? What puts the line in here? The train points, but all of them, right? The classification of Z, if I use a linear regression function, is determined by all points. So suppose this is pluses, 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 pluses. And I have a bunch of minuses, minus, 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 minus. The position of this separator plane, it's dictated by all those pluses and minuses. Whether it's support vector machine or a linear regression, it's still all of them that contribute. I mean, support vector machines have a way to say, I'm going to select the closest one to contribute, but that closest one has nothing to do with Z. Closest in support vector machines, the closest point is support vectors. are the one close to the plane. So my point is, this is not a local classifier. This is a global classifier because it looks at the whole training set and does the best it can on that training set. Right? I mean, we've seen this, the same thing applies to naive Bayes or any other classifier we've done, neural networks. So this is a global classifier because I can't change the position of it based on some small area on the data space. Right? Discriminator have to apply to the entire space. On the other hand, the neighborhood of Z, this neighborhood that I'm talking about here, the closest points to Z by some, we didn't describe the metric yet. We'll have to figure out what closest means. But the closest classifier, right, is going to be something around Z. It's going to be all the points that fit in there. Maybe there's 3 pluses and 2 minuses. Why is this a local classifier? My decision in here will be purely based on that on what's inside the neighborhood. So I'm not going to be influenced at all by the rest of the data points, which could be a lot of data points. So what's the advantage of a global classifier?
It handles outliers better.
It handles, you mean points for which, not necessarily outliers, I think you mean points for which there is no good neighborhood. Like if I have a point somewhere in here, outlier, I mean, depending how we define it, this may not be an outlier, maybe a negative point, right? It's not an outlier if it's a negative point. There's nothing wrong with it, it's nothing unusual. But there is no neighborhood around it. These classifiers, the global classifiers, will have no problem to identify this as a minus. Because it will be like, based on what I've seen, this patient is clearly on that side, even though I haven't seen many patients like this. So what's the advantage of a global classifier is I don't need to have seen points like this. I can make inference based on other points in a global sense of the space. I'm looking at the entire space and I'm saying, this is my best guess for how to split it. What's the advantage of a local classifier?
If it does have a good neighborhood for a point, then the prediction is probably going to be really good.
Right. But why would the, so I think he's saying if I have a neighborhood that's very, very dense, I have a lot of neighbors, so a local classifier could do a good job based on all those neighbors, assuming I have, say, voting or majority, whatever my heuristic is for prediction. But what's the case in which a local classifier cannot handle this problem? So why would, in this case, we would like a local classifier as opposed to a global classifier? Anybody looked at homework 8? You see those spirals? So I'm going to put that drawing on a projector. That's the answer to my question as a picture, but what's in English the answer? Right? If you look at those spirals, they're exactly the answer to the question I'm asking right now.
If the neighborhood is mixture of 2 classes.
Or more than 2, doesn't matter 2 or not. The point is, I have these neighborhoods which are dense. If you look at those spirals, the neighborhoods are extremely, extremely dense. But not in a way that the global classifier can make a separation. So I could answer for each point. Of course, in this case, as drawn on the board, if this is a negative and all these guys are negative, both global and local classifiers will do the right job, right? Both of them will predict negative. But what if I have a bunch of neighborhoods like this? Here's another one. Here's another one, and another one, and another one, and another one. And they're not organized in a linear fashion. This is minuses, this is pluses, minuses, pluses, minuses, pluses, so on and so forth. I have those density regions, which are, say, my patients' classes or you know, types of treatments that I want to do, who knows what. They're not necessarily linear, but they're extremely dense. That's when a local classifier can do much better. Also, a local classifier, I'm going to get back to this later, has the advantage that it's robust in terms of assumptions. I don't need to make strong assumptions to use a kNN, right? Well, a lot of the classifiers we did, the global ones, had some assumption, right? Data has to be Gaussian in nature. Data has to be linearly separable, so on and so forth. Typically, local classifiers have a lot fewer assumptions. About data. Yes?
In the same problem, can't we have, for dense regions, can't we have a support vector machine and a Gaussian kernel to solve that?
Yes. So we need to find more interesting examples to track that one. But still, even that makes some assumption, right? There's some Gaussian kernel that makes the data separable, and the support vectors can be found, and so on and so forth. It's not too hard to take any such assumption, whether it's the neural networks or the support vector machines or trees, and figure out how to break it. And once you break it, you can easily invent a data set that kNN will work. Because for kNN, the only thing you need to make it work is some neighbors. If you construct a data set that say support vector machines don't do well, how do I then make kNN do well on that data set? All I have to do is to add for each point few neighbors that have the same label, and the data pattern or shape will be the difficult one that support vector machines don't do, but my kNN. So kNN, again, is very robust in terms of data assumptions, shape, but it only works if you have neighbors. If you have neighbors, you're good. It doesn't matter how difficult it is, how hard it is, how spread it is, sparse, as long as there's neighbors, kNN will work. And very simple too, right? I mean, what does it take to do this, really? We have to compute a neighborhood, so we have to figure out how that goes. But then there's no really the training phase here. I don't need to. The training phase, what I might want to do is a pre-processing step to facilitate computation. If I go naively and say compute all pair similarity, you know, if I have 1 million data points, that may be a huge number of pairs to compute similarity. But other than preparation for computation, there's no training. Compute neighborhood, predict the label. This is one of the things that as a data scientist, I would try very early on. Like I said many times during this course, the data scientist job usually comes down to something not working. Very unlikely to make a lot of money by just calling packages and getting results straightforward. So you're gonna be called as data scientists when something is not working. And when you are called, you should run kNN first before you even, you know, dealing with that. Because kNN will give you some very good inside information, as in, are they neighbors? Is it the case that every patient in my data set has a good neighborhood in the training? Even though the hospital you're working for is not using kNN as a classifier, the insight that for every patient or for every difficult patient, you already say you run a neural network and you know what cases are the ones that you have a failure, a high failure, you don't do well. What I would do, I would run the kNN and say, for these cases, how many similar patients like this I've seen? Is it like 1 other, 2 other, 10 other, 20 other? Like you'd expect, difficult cases are probably the ones that you don't have enough data for. That's what makes them difficult. But nevertheless, it's a good experiment to run and pretty simple. Yes?
Won't kNN perform badly on the points that are closer to the line? Because it will take into consideration.
Right. But that's so to answer the question exact, not necessarily. His question is, wait a minute, if I'm in here and the point is about here and you have roughly like 6 minuses and 6 pluses, the chance of getting the right label here seems pretty random, because you have a lot of pluses, a lot of minuses. Some of them you might get right, some of them you might get wrong, right? My initial answer is that probably every classifier will have that difficulty, right? If something is close to the boundary, it may be that there's an intrinsic reason for which it's close to the boundary. As in this patient, we can't really tell if it's sick or healthy. It's like in between. Any classifier will have trouble. But this is not necessarily the case, right? Because the question has to do with close to the boundary. Close is not well defined here. What does it mean, close? I mean, for some data sets, close might be here, this is closed. Yet in that neighborhood, I have 90% pluses. Or in some other data sets, close might be here, and I only have 60% pluses. So I think to answer this question more technical, we need to know what does close mean. The more technical answer to this question is that what he's bringing up, more or less, this question, is the notion of density. So this k nearest neighbors, the part that we've already said here, is the easy part. It's the one that says, okay, I knew that since high school, kind of like, if I know what other, homeworks or what other patients or what other emails are like the one I'm looking for, I could tell you what you want to predict. This question here has to do with the notion of density. How do I measure this kind of probability of something happening based on the evidence in a neighborhood? So that's a well-known question, and it has to do with this kernel density estimation subject that we're going to get to. Now, are we all on the same page here? I think this is pretty basic, and everybody knows this. Right? Before we move on, how do we compute the neighborhood? Essentially, two big ways to compute a neighborhood, right? The one way is to say the neighborhood of a point Z are all the points X with the property that some distance between X and Z is smaller than some threshold. This is based on range. It's saying that everybody who's that close to my point is part of the neighborhood. Or the other option is kNN k of Z. I have this parameter k here. It's X in the train, and X is top k close. That is, if I sort by distances, X would be one of the top k. If k is 5, sorting by distances, then I have top 5 neighborhoods. So this is fixed size. Fixed size. But this variable range. And this is fixed range, variable size. So what do I mean by this? For the first one, everybody has the same radius. If you visually look at the neighborhood and say, here's this example here. Everybody has the same range. We can call this R. But what do I mean by variable size? In here I may have 5 neighbors, or 6. In here I may have 2. And in here I may have 100. Because I fixed the range. I could catch in that range different number of neighbors for different points. Now in here, this one here, it's a fixed size. Everybody has 5 neighbors, right? K equal 5. So there's 5 things in here, but to catch 5 things for this other guy, I need 1, 2, 3, 4, 5. So the range of it is not determined, but everybody gets 5 neighbors. Which one's better? That's not clear. It's not like always one of them is better.
Can you do a union of the two? So the nearest 5 and then
Sure.
also everything in consideration?
Sure. So I can have the closest 5, and including at least 5 and up to some range. All right. So that's kNN in a shot. What you should think about is computational aspects. The mechanism here, the algorithms are very, very easy. Just what do I need? I need this distance function that I can pick Euclidean distances or any other distances I like. Dot products, kernels. Like, can I use a kernel here? as a similarity function. I'll have to say instead of smaller than, bigger than, like a kernel serves as similarity. But I think I can plug in any kernel, and based on this kernel, can I do this too? Sort by the kernel values and pick the top 5. Okay, so I have to pick that, but then to do these operations in here, how often and how many distances I have to compute, right? So that's could be easily a problem, right? So a lot of latest research in nearest neighbors focuses on how many nearest neighbors I need to compute on. It would be nice to have the support vector machine idea. If somebody would tell me something like the support vector, I don't know what that means yet, but if somebody would give me the support vectors, so I don't have to compute similarities against the entire training set for everyone. Maybe that would be better. By the way, I don't think it's n square, right? So it says I have 1 million training points and 100 test points. How many similarities I need to compute? Do I need to compute the similarity between the train points? At least not in the basic version, right? So I need for every test point to compute similarity with the whole training set. Now, can I use some sort of, maybe some helper, like a regression function or a support vector machine function, to not compute similarity for a test point with all million training points? Right? That's the killer that computationally kills this process. For every new patient, I have to run this patient against all my million training set. So I would like not to do that.
You can cluster the training set.
And then I still have one test point. How do I do the similarity?
You pick a representative from each cluster, compute the similarity of the test point with the representative, and then you use that as this kind of standard value.
But maybe I have to weight that somehow to the size of the cluster. Okay. But my point was, if I have a helper, maybe that works, but if I have a helper like a classifier, global classifier, which is not very good, it may give me the wrong prediction on my points. There's a lot of points that I could get wrong prediction, but could it at least give me what are reasonably to be the neighbors. So say, I got this point Z here, my regression classifies it as a plus, that's fine, but can I tell which other points I need to compute similarity with?
So you told we can use SVM to get the support vectors, but won't we have to do that for each point or to find out which are the supporting?
I didn't say SVM, I'm just saying something like that.
Okay.
I'm posting questions right now. I don't have answers for those questions yet. So we all know, I think, we can agree that computing this pairwise similarity is Achilles heel here. So how do we solve it? We don't answer that now. I want to pose this question, and you guys get to the homework, and we'll get back here on Thursday and see if we have an answer for it. But this is typically the problem with k-NN neighbors. How do you do it fast enough, especially for large data sets? Suppose I move from, I have MGH. How many heart surgeries are at MGH? Not that many, right? How many patients have that? 400, 500, 1,000, 2,000. Not a big deal. But what if I'm Amazon? At my products or my customers, that's too many to run similarities against a base of 300 million items. All right. So that being said, let me erase this here. So I want to do two things. One is a heuristic for feature selection. I don't think this is used a lot, and you don't have to use it. But I want to bring an idea that we talked about 2 homeworks ago. What is being useful when we compute those margins of features for boosting? If you've done that homework, how do I look at what features being very useful? So what I have here is to say I'm looking for a feature that is useful for discrimination. By label. So so I'm going to apply this quality quantity for one data point. Let's say Z, because we start with Z. But Z in here is a training point. So here's X, and I'm looking at X, say that's a plus. And there's other pluses here, and there's other minuses here. So I want to think of a feature. I want a feature to discriminate between the pluses and minuses, right? So I have Z. Z same. Same class as X, and Z opposite is opposite or different class as X. And for a feature to be good, this value xj minus z same. So this is x. Any other plus could be a z same, and any other minus could be a z opposite, because plus is same like a plus, minus is the opposite. So how do I want this value to be? The difference. So this is looking at only one feature, if you remember the data table. I'm looking at X and I say X has the label red. Z same means Z also has the label red. But I'm not looking at the whole vector, I'm only looking at the feature, particular feature, like feature number 4. That's the J. For this to be useful, if it's the same, how do I want this difference to be? Small? Right? To say, okay, I go by that feature, things that have the same label have reasonably close feature values, only on that column. And how about the distance? Again, I'm looking only at that column, the 4th column in the data, between X and red versus a blue or a green here. I want this distance to be large. So that's the concept. Now, of course, I have to create some mathematical function based on this concept, right? I want to say sum up over all the data points to see overall what's the feature that's useful. So there's a formula here that says the quality. This is an updating iterator formula. So this is iterate over x z pairs. it's kind of subtracting the ones that have to be small and adding the one that has to be big. And I have to do it over multiple data points. And I have to do it over potentially for one data point. I have quite a few Z same and quite a few Z opposites. So that it's a reasonable heuristic for feature selection. That's saying, you know, overall that's going to tell me how good the feature is. If I run this loop enough times, I'll have a notion of what feature corresponds to label. Now this is a priori feature selection, so it's not aware of the quality of the classifier, but something that's easy. Back to this, I'm doing it in this way because the nodes are in this order. In here, so I erased this by mistake. Let me put it back. Here's one notion that this guy had 5 points, right? And then we say it's possible that a different point to have 5 neighbors, I need to create a much bigger neighborhood for it. That was the second option. I would like to introduce a third option. I like to say, what's the obvious disadvantage here again? If I force a range, say everybody that has, you know, within the range of 20. No, many neighbors usually not a problem, right? But it might be computational or it might be something related to smoothing. But fewer neighbors, definitely a problem. What's the problem here?
Neighbors can be at a large distance.
Right, so the range might be way too large to be useful. If somebody doesn't have neighbors and I have to go all the way to the periphery of the data space, that's probably not useful information to. Right. So how can I do this in a more like smooth way? I'm saying what I mean is, even here, I would like to say these points are closer neighbors, like they should influence things more, and these other points at the extreme are far away neighbors. They influence things less. So I'm trying to solve both problems in the same time. The problem here again is I may not have any neighbors for some points. The problem here is that I can get neighbors, but the range is too big. Now, there's nothing I can do about data. I can't move the neighbors closer to X, right? That's not the solution. What I can do is to count things, weighted them to be smooth. To say, okay, I don't know how big the neighborhood is. Maybe it's this size, maybe it's this size. But I want really close points to be really important neighbors because they're very, very close. And faraway points to be not so important neighbors. That way, I don't have to have a fixed range or a fixed size. I could say, everybody's a neighbor now, right? I could say, here's a data point. The entire training set is a neighborhood, except the closest points are much more good neighbors than the faraway points. So let's introduce this option here. kNN of Z is the entire training set, but weighted by similarity with Z. So my notion of neighborhoods now is not the top 1, top 2, top 3, nor something whoever's close in a range. It's everybody is a neighbor, but not everybody is as close as a neighbor. So let's see what's going to happen. So I have my point Z, right? And I have another point is x1 that's very close, and I have another point that is x2 that's farther. So what I have here, the distance, I'm going to use the kernel notation, but it could be any similarity function. The distance between Z and x1 is high. Sorry, the similarity, right? They're very close. And K is a kernel or similarity function. and the distance between Z and X2 is the similarity, so it's low. So how could I use this now? Weighted. What does weighted mean? I want to count the X1 much more than I count X2 as a neighbor. So, I mean, depending of what kind of heuristic I use to do predictions, I have to change that heuristic to include those weights in. What do you mean so far? Okay, let's do a little recap. This third idea, I hope everybody got on board with the first. The third idea is to say, maybe it's not a good thing to set in advance the range or the size. The size is how many neighbors you want to consider. The range is up to what similarity value you consider something a neighbor. There are additional problems with this range that saying if I have a very dense neighborhood, is it really the case that this point is a neighbor and this point is not a neighbor? Like they could be so close in there that's hard to tell, include those and not include the ones that are immediately out of the line, right? So what we want to do here is to create some sort of smooth space of the neighbors that includes everybody, right? And we'll definitely solve these problems. And we'll definitely solve the how confident I am in terms of predictions. In kNN, regular basic kNN, I don't know if my prediction of say salary or house price comes from averaging 100 things or 2 things. The average might be correct, but the confidence is very different. If I have 100 houses to average by, I'm much more sure about my prediction. But if I have only 2 houses, that may be, like an area where I don't have evidence. So I want to solve that problem too. Say, how much averaging do we do? So every point in here, data point. In here, every data point that's a neighbor, that's X, counts as one if in neighborhood and 0 if not in the neighborhood. Right? It's either in or out. In here, every data point counts as k of xz. So there's no 1 and 0 anymore. There's not in and out. Everybody's in, just with different weights. So how's prediction gonna go? Probability of x given a certain class. You can call those n now. So we're gonna say, if you pick a class, the probability of observing such a point is dictated by some summation over these similarities, right, of k of x and z in that class. So we have to assume something about k here and some probability interpretation. This NC is the number of data points in that class. So probability of the class, that's a prior, is NC divided by N. N is the total. Probability of a data point, I'm going a little bit back to the third module, generative models. But these are very simple Bayesian equations. So I have three probabilities here that I need in the Bayes formula. One is probability of seeing a point, that's a density estimator. This is a prior probability of seeing diabetes patients in a house. And this is a conditional density, that's saying if I only look at a particular class, diabetes patients, what's the chance of observing this patient? So how, I think this is very easy to follow, right? It's a normal ratio estimator. What about this? What is it saying? So when is this value high? How do I get this P of X being Z to be high?
When there are more data points in one class and they're all clustered together.
So all those Z's, right, that I'm considering here, there's another whole training set. I'm only considering the Z's that have that class. Right? So suppose I have three classes, red, blue, and green. I pick an object X, that's a, something that has a color. And I'm saying, let's look at the green objects. How many greens objects you have? You have 100 things. So divide by 100. And then sum up the similarities between my object and all the other green objects. So for this to be high, the similarity with the greens, so a probability interpretation means this case between 0 and 1, say, right? So if I have high similarities in there, it means it's similar to all the greens, so I get the sum of this case will be close to NC, divided by NC, I get something close to 1. No, ends up with follows me, so we have the sense. Okay, so again, what am I doing here? I'm saying I want to measure what's the chance that X is green. Look at all the green points, sum up their similarities, divide by how many there are. That's kind of the average similarity between X and the other green points, or between a patient and everybody else that has diabetes. But I'm not measuring similarities towards the other classes, just with this one. Now that I have these three, of course I can do the Bayes formula, right? So this ends up being, I skip some steps here. Y Z equals C D. It's a very intuitive formula here. It's saying you want the backwards base here, instead of getting the probability of seeing an X within the diabetes space, it's saying the probability of having diabetes given a certain patient. That's the classifier, right? That tells me how to predict the class, right? I'm probably gonna predict the class with the highest probability, like R max. What this formula, after some calculation, gives me is saying you gotta sum up the similarities of everybody in the training set. And think of that as a whole, as the whole pie. How much of a chunk of that pie? This in here, let's draw a pie. This is the whole pie, which is this, the whole bottom. And this is saying how much of that pie corresponds to similarities for that class. So this is how much. And that, of course, this is a probability space because you can see if you do it for all classes and you sum it up, they're going to sum to 1, right? They're going to normalize. So everything in here, it's a class. And this now it's weighted. Everybody participates in this formula, every point in the training set, but not as a 1-0, either in or out. It's a small thing. Points very far away from Z they will have no contribution, right? Because the numerator and denominator were very close to 0. Whether I include those points or not, I'm pretty much getting the same thing. Points that have high similarity with Z, they're going to contribute for both numerator only if they have that class. So I'm smoothing it out. And now I don't have to worry about how many neighbors do I need. Do I need 3 neighbors, 5 neighbors, 10 neighbors, 20 neighbors? Because everybody's a neighbor. Or equivalently, I don't have to worry about the range. What the range should be. How far away I'm considering something to be similar. Because in this version here, fixed range, I'll have to decide in advance my range is, suppose I use the Euclidean distance, say it's close, whoever is, below a fixed value like a 1 or 2, depending of size of the space. If I use like a cosine distance, I'll say whoever have a cosine bigger than some value, maybe 0.8, that's a close enough neighbor. But I have to do trials and error. Both those things depend on some parameter, number of neighbors, k, the range value, v or theta. And this parameter, it's hard to set it up in advance. It's like the regularization parameter. You gotta do trial and error until you figure out the one you want. This also depends on the parameter, but it's much more hidden. In kernel density estimators, the parameter that's here, it's called kernel width. Or there's a, before people formalized this notion, there was an equivalent thing called partisan window. That'd be the size of the window that's being used. Now, this kind of notion here, it's very similar to the problem of if I want to estimate the probability density function. So think about that. Just a discussion parenthesis here. I want to estimate a probability. This is the x, the space, and this is p of x, right? The probability. And my density, maybe something like this, right? I want to estimate for every point what's the probability. Now, what I do sampling. I don't actually have access to this, but I have access to data. So I'm going to get some sampling points, and depending on a certain space, right? How many points I've got? If it's a lot of points, my estimator from here will be a high frequency, right? That's how histograms work. So what do people do? They build a histogram, right? They say if you ask MATLAB or SkyKit, right, to give you a histogram for data, it will probably build a histogram that says, okay, well, let's split this range into, say, 10 things. I think 10 is default for histogram in all programming languages, default option. I have 10 buckets. And say, well, this is high because you have a lot of points that fall in there by sampling. And this is 1 point, it's very little, that's 2, that's high. And you start getting something that more or less looks like the probability you want. Of course, it's pixelated because any sample is a discrete sample. Whether you pick 100 points or 1,000 points or 100,000 points, you still have a discrete representation of that space. It's still not a continuous curve. My point about this is who decides the buckets of the histogram? Either by the number, say 10 buckets, which means take the space, chop it in 10, or by the how much you want the bucket to be, right? You can say I want this bucket to be 0.05, and then my range from min to max divided by 0.05 will tell me how many buckets you actually have. So let's continue this thought for just a minute, because this is extremely important in all the data estimators. This is an absolute critical question in terms of getting the right estimation for a function with a small sample. What happens if the bucketing is too small? Like I really pick the buckets very, very tight. So I'll have a lot of buckets, right? What's the problem with that?
No one was under this.
Most buckets will have nothing because they're too small. And the ones that have something, they're gonna appear very high. So I'm gonna get some frequencies that are too high and many frequencies that are 0. What happens if the bucketing is too loose? Like I only have 3 buckets. I redo this exercise and I say, look, you have from min to max, you have 3 buckets. I'm going to get very good estimators now because there's a lot of data in each bucket. There are not that many. But I only have 3 points to estimate my whole function. I'm only getting 3 values, right? I won't know the shape of this distribution just from 3 numbers. Now the other one with a lot of buckets will get the shape right if there's enough data in all those buckets, right? If every bucket has the right amount of data, we'll get the frequency, the discrete frequency, discretization, how it's called, right? Problem is, I don't have data to populate all these buckets. All histogram estimation, which is not the only way to do it, but all these histograms, to be useful, I'm talking from a practical perspective, they gotta get the bucketing right. If you get too many buckets, most of them will be empty, and everything looks very black and white, either full or empty, because a bucket would either contain a point or not. If you get too few buckets, the frequencies are correct. It's just too few frequencies to estimate a complicated function. Right? If I knew this is kind of a flat function, maybe 3 numbers is enough. But if I have a complicated density here, probability density function, I can't do it with just 3 buckets. Right? So this bucketing, it's exactly the problem of setting this bandwidth of the kernel here. That is, when I measure the similarities, how many points I'm looking at. It's the same problem like in here, but that's a discrete version of it. What's the right number of neighbors to look at? Sorry, that's in here. And the same problem in here with what's the range that I'm dealing with. A lot of data problems comes from sparsity problems. It's very unlikely you're going to get a data set for which everybody has good representation and good neighbors, and somehow the machine algorithm failed. I mean, if that's the case, there's some randomness going on, like the labels are not corresponding to the features. Whoever puts the annotations there or the targets, the feature representation is not useful for them. But most of the problems are not like that. Most of the problems are due to sparsity. I have a lot of patients that requires unique treatments, and I can't learn because there's only one kind of that thing. And then this is what's a typical problem for a lot of generative functions. So now, next time, I think we can talk about this thing. This effectively is the last thing we need to do for the course, so we have one day tomorrow, Thursday, to talk about anything we want. So one thing that I'm considering doing is to expose you guys to this kernel density estimator, that it's more useful and used for estimating probabilities than to set up the right kernel similarity function. See, in here, in practice, what people use is a domain knowledge similarity. In the kNN space, people don't bother so much with the theory. A doctor or an image, graphics person or somebody who deals with text, they know what kind of similarity they need. So they will plug in that function, and the only problem here is computation, right? How do I deal with the fact that I have now the entire training set as my neighborhood, so I'll have to deal with those computations. So how about we look at that figure for a little bit? Actually, I have a few figures to show you. That's the one, right? Of course, this is created artificially. For people who have looked at HomeOK, they have seen the figure. Maybe they knew the problem, but they looked at the figure. It's easy to tell no classifier will do this, right? No linear classifier can solve this problem. So I think the actual problem, the homework, relates to perceptrons. It's what we talked about last time. A perceptron won't be able to do this because it's a linear function, but if I apply a kernel to it, it could do it very well. And that's a very easy problem. I mean, it has fancy names and terms in it, but the reality is if you run perceptron, any perceptron, you can try to run for say 100 rounds, 1,000 rounds, how many rounds you want, you're gonna get pretty much 50, because any linear function will have half errors. But then when you plug in a Gaussian kernel, which is the zoning local kernel, it will work well. Not because there's a spiral, so the shape of the data doesn't matter here. A zoning kernel will have the effect of kNN, like somebody pointed out, would be like be able to isolate those regions. The zoning kernel actually should isolate more than just a neighborhood. Depending on how you set up the kernel, the Gaussian kernel, you may get bigger regions in here. Now, what about kNN? What would kNN do here? Would it work? Will work very well, right? Because what makes kNN work so well? This gap between red and green, right? This gap is essential for kNN. For Gaussian kernel, there's still assumptions, right? Like what Gaussians can cut out of this data space, or any data space, would be Gaussian regions, which are nice, big, oval things. A kNN has no assumption about oval or non-oval or convex, non-convex. It's gonna say for every point, look at the neighbors. What it needs to separate the good neighbors from the bad neighbors. Like for a green point, the good neighbors will be the green ones, and the bad neighbors will be the red ones. So what I need to set is some notion of width of that neighborhood that respects this gap. By respects this gap is, if I set up the width too big, say I pick a green point, and my neighborhood includes a lot of points, I haven't achieved anything, because in that neighborhood I'm gonna have greens and reds, and I can't tell whether the point is green or red. That neighborhood does not respect the natural gap between green and red. Now, of course, if I put it too small, if I make a circle that's extremely small, I'm not respecting the density of the greens, because I'm not including any other greens. If the neighborhood is extremely small around the point, there's no advantage in having those green points around. I'm not going to include them. So a good neighborhood is the one that kind of includes enough greens, but doesn't go too far to include the reds. So because this is artificially generated, it's easy to find that gap. Either you go by range or you go by the size, how many points you want. You know, you can guess from here, if you go to like the close fibrous points, those will be the same color. And if you go by the gap, you can probably, with the say Euclidean distance, tell which gap is the one that will separate the two. But of course, data in reality is not that easy. So for kNN, you can the basic problem here is say you use the basic data set you've seen before and implement basic kNN and try different k sizes, 1, 3, 7, so on. So you can try more than this. I have another picture here I want to show. How about this? So this is my data set, is the same data set, right, in all three pictures. Which one is, without knowing what's going on here, if I tell you I want to classify things, which one is, do you think, the right classification?
What is the one on the right even mean?
This one on the right is the same as the one on the left. It just has colors for when things get close to the confidence
It's
colors.
like 6
right?
out of 7 or whatever.
Right. This is saying that I'm super confident on the sides, and there's a notion of how many neighbors or some regression over neighbors or something that says, you know, the yellow ones is when I'm not sure because there's in that neighborhood there's all kinds of things, right? It's kind of 50-50, and the more I go to red, it's more red, right? The more I go to green, more. But my point is, if we go to this level, right? This is those Voronoi diagrams that will essentially take this whole space and split it exactly into what's the region of every point in here, and the lines between the regions are exactly the geometrical perpendicular lines that separate the points. We need a proper, the difference between this and this still comes down to the size of the neighborhood, how we look at it, right? Again, like somebody pointed out, this is close to what an RBF kernel can do, except RBF kernels are much more full of assumptions about what they can cut out of the data. The kNNs don't have these assumptions. They can cut any region out of data, just like the decision tree. And I have another picture here that I'm going to show. I may end up drawing it on the board, which is people have thought about this slightly from a different perspective. Still local classification, still based on similarity function. So let me put the problem in this way, which is I have some representation of my data. This is based on the digits that you've seen, but they could be patients or emails, just the same. I have some label points. The label ones are the ones that have a blue label on them. 1, 0, 9, 4, 8, and 2. So the other ones, I kind of don't have the labels. And with local classification, I need the similarities. The similarities are represented here conceptually for illustration purposes as those lines, like, you know, it's a 1 to 7 line because they're kind of similar, and there's no line between other things because they're not similar. That's just for illustration, because that's not what's happening, but I have to represent somehow what I think is similar, what is not similar. So what I have here is the entire data represented with some labels and some things that I have to predict. I have to predict the 2 and 3, so on and so forth. And I know who's similar with who. So I'm kind of creating a graph, right? More or less like Facebook. I know some things about some people, and I know who's friends with who. And I would like, based on this graph representation, to kind of propagate my label. In other words, I would like to say, can I compute this tree as an average of what's already labeled? The tree is hard because it's in the middle, but maybe this one here it's easier because it's closer to some labels. So what I'm trying to do here is to take the concept of local classification, that's kNN. kNN, it's also called instance-based, right? If I have a Z test point, I'm only concerned about what's around Z, nothing else. I want to take that concept and say, well, if 6 is related to its neighborhood, and this 3 is related to its neighborhood, and this 4 to its neighborhood, and so on and so forth, can you make this a smooth space overall? Like, I don't want to treat these instant classifiers as separate problems, right? The kNN treats every single Z as a separate problem, computes a neighborhood, computes a prediction. And here I'm saying I need to compute kind of all the labels in a local way. I still want a local way. I want this 9 to depend on its neighbors. I want this 6 to depend on its neighbors. And I want this 2 to depend on its neighbors. But overall, they have to kind of not contradict each other. Right? Like if I say I think this one is a 2, and this one is a 4, and they're very close to each other, something's wrong with my prediction, right? So how can I make this instance classification work for the whole space? That's the problem here. This has been a breakthrough. This idea was a breakthrough in machine learning about years 2002. Not easy to implement it, but was a completely new idea. And here it is. Again, I want to make sure we understand the data representation. I have some data points. I have some of them labeled. I know this is a 1, a 0, so on and so forth. And I have the notion of similarity, at least the ones that matter. See, not all lines are drawn in this graph. This is kind of a threshold there. It says whatever is higher than a similarity has a line, what's lower doesn't have it. And the purpose, again, is to populate the whole space with labels, classify or predict a label for everyone in such a way. There's 2 constraints. Every label, first of all, has to be an instant-based classification. It has to play well with its neighbors. Every instance has to be an average of its neighbors or a majority. That's exactly the same notion we have kNN. We want to respect the nation of a local neighbor. If those guys are all 3, 3, 3, 3, 3, the one in the middle has to be 3, 2. Because you can have all the neighbors being 3 and you not being a 3. But we want all these classifications to kind of play well with each other, not contradict each other. Yes?
What would it be to contradict each other, right? Which means that if you put something among a bunch of 3s, then that's just 3, 2. Like how we are.
So that's the first one. Everything that has a consistent neighborhood of 3s has to be a 3. But then how is this neighborhood placed well with now another neighborhood? And another neighborhood. Because I may have multiple neighborhoods that have common points between them. So I want to treat this not as a instance-based objective. Again, the prediction has to be local-based, but overall I have a global objective that I want to optimize. So the breakthrough to this problem came from a notion of thermodynamics, and later on has been shown that's equivalent to graphs. Because the graphs, the thermodynamics is well known for a long time, but graphs, there was a lot of research in graph theory and these kind of problems once Facebook became very popular. They have a lot of research into graphs, so that happens later on. But the thermodynamics, which is extremely intuitive, is to say all those points are physical points in this room. So your heads, for example, right? The physical points. The distance, it's obvious. What is the distance? The similarity. If every one of these points represents some physical space in this room, effectively where your head is, what will be similar versus non-similar?
Distance.
The distance, right? You're close to him, but not close to the gentleman in the back. What is labeled are called heat sources. This is the window, this is the radiator, this is the door, and this is the AC. So what we're measuring here is temperature in thermodynamics. Every point, every one of your heads senses heat, right? And what does it make some points be more cold or hot than other points? It relates to where that point that I'm measuring temperature is, how close is to all the heat and cold sources in the room, right? A point close to a window will be colder because the window is a cold source. A point close to, whatever the heat source is will be warmer because there's heat coming out from there. Everybody can see this in a common sense way. Now, the reason this idea of thermodynamics called heat equation works so well for this problem is because heat, it has stability, or equilibrium is called in thermodynamics, with respect to distance, to local classification. It turns out that the law of thermodynamics says the temperature in any point you pick in this room has to be the average of the temperature of the points around. Repeat that again. I pick a point here, the corner of this monitor. If there's 70 degrees right now in this corner, I take a neighborhood of other points around this corner, take the temperature in all the points in that neighborhood, they're going to average to 70 degrees. It's a law in thermodynamics that says the heat, once it becomes in an equilibrium, aka, when you open the door, heat changes, temperature changes in the room, right, or you open the window. But when it becomes in an equilibrium position, like temperature doesn't change anymore, like right now, there's not much change in temperature until somebody opens the window or the heat starts or the door opens, right? In an equilibrium position, heat must respect locality. That is, if his head is in a cold region, you take a neighborhood around, take the average, that's going to be a cold thing. You can't be in a cold spot if your neighbors are all hot. You can't be in a hot spot if all neighbors are, the closest neighbors are cold. So that comes from thermodynamics. This rule was known for a long time in how heat propagates. So then what people said, can I use that sort of mechanism? The way, if this is the door, the window, the AC, the heat source, the radiator, so on and so forth, how does heat propagates to some particular point in the room, like the monitor? What's the rule that dictates the temperature here, given the distance of this point to the other points, and eventually to the heat sources? How does heat propagate? So people took that idea, call it heat equation, heat kernel, and apply it to machine learning. And say, if you know the rules of thermodynamics, can you apply them to data? Turns out you can. And you need to define the similarity. That would be an exponential, sort of like RPF kernel. But it could be other things. And then there's a heat equilibrium equation that comes from thermodynamics that says, in order to have stability, in order for the heat to kind of maintain a constant temperature, like it reaches an equilibrium position, it has to minimize this equation. So there's a theorem that says many things, but one thing it says, when you reach the equilibrium that you want, that will be the labeling for us in machine learning. You need to have the minimum of this function. The minimum of this function, we've seen it before, this function, or maybe you've seen it more when you do k-means. We didn't do k-means in this class, but if you do k-means, you've seen this a lot. This is called an energy function, and it says f is the label here, and k is the similarity. So what this says is, I'm going to penalize, because I want to minimize this, right? What's a big penalty? When do I get a big penalty? When things that are very similar, like 2 points next to each other for the heat problem, have very different temperatures. So this is a penalty on energy. Energy in thermodynamics is the opposite of equilibrium. When things are in equilibrium, there's low energy. When things are high energy, they typically tend to get out of that position. Right? They're not in equilibrium because there's high energy. That typically means things are going to change. Right? So this, to satisfy equilibrium for heat, that is not changing the heat anymore, it says that I need to have minimum heat energy. Heat energy comes from having things that are close to each other. They have high similarity, this K, but very different temperatures. In other words, this equation says, if these two gentlemen here, they're very close, but their heads register very different temperature, cold and hot, we're not in an equilibrium position. It's very likely this will change. This is not where the heat is going to settle. It's because somebody just opened a door or a window or the heat started, but things are likely to change. On the other hand, if this is very, very low, it means that when things are close to each other, they have to have very small difference. By the way, this is now a typical regularization term for many problems, not related to heat equation, that says, word vectors kind of work like that. Again, we didn't do word vectors, but for people familiar with it, say, if two words are very related, very similar, very co-occurrent, very whatever you want to set them up, right, in text, you want their word vectors representation to be kind of close. So this is a regularization penalty now used in other problems. So the theorem that I'm talking about from thermodynamics says the equilibrium of heat has to minimize this function. So that's what the machine learning people did. They say, why don't we minimize this function? But there is an important result that's the equivalent of KKT duality, that says the solution for this equation, it's always an average, a weighted average of the neighbors. That is the thermodynamic rule that says in an equilibrium position, every point must register temperature, which is the average temperatures around.
So is this like, previously when we wanted to like show that we made the right decision for our model, we would say, make a maximum likelihood problem and show that this specific choice maximizes likelihood. Here, are we making an energy problem and showing that it minimizes energy?
That's a goal. We don't show anything. We say we want to minimize this function, but we use the result from thermodynamics that says this equation is minimized. So KITs are given here. The similarity between the points are still assumed that we can compute those. What we're looking for is this f function. So the f is the variable, and the equation, the heat equation, says that the solution for this problem is unique, number one. So once you have it, that's the one. But more importantly, it says that f has to be the average of the neighbors, which is exactly this heat law that says heat at any point has to be the average of the heat at the closest points to it. Yes.
So because of that heat law, could you just make a copy of this network and then for each point of the original, just take the average of the ones that are linked, that are in the neighborhood, and then just basically update what's in the copy?
Right, so I don't need a copy, that's for implementation purposes. What he's saying, can I do this step by step, right? Can I just, I have some labels, take an average, compute the next one, now I have that one, compute the next one, so on and so forth.
Because as you change them, you're changing what the values of what's connected to them are.
The problem is sometimes I may have to go back, right? I mean, not all networks are organized in a way that there's clearly a path, greedy. You're describing a greedy path forward, right? Where in this network, where do I start? Like if there is a one neighbor that has all the neighbors already labeled, then I can easily compute the average for that one and then move on. The problem is I may get to a point where I don't know which one to compute first. So this is trying to satisfy this from a more global perspective first, at least the theory. What I want to emphasize here is, can everybody see that this is a weighted average? So F is the value of temperature at point xi. Maybe I should make this a little bigger. So F is the value at temperature at point xi. Ft, T are neighbors, right? So Ft is the value, F of xt is the same thing. Ft is the temperature at point T. But it's weighted by how close that point is to I, right? So that's exactly the same thing we had here when we said we're gonna go by this kxz to weight the points that matter. So in here, some point that's very far away, KIT will be very low. It won't matter what the temperature at that point is. But if the point is high, KIT is a close neighbor T to I, then that temperature will contribute a lot to this average. And then DI is the number of points around. Okay, so like in a graph sense, will be like how many neighbors I have to 1, 2, 3, 4 neighbors.
Professor?
Yes.
I'm not sure I really understand, because what I was trying to get at was, could you avoid basically having to continuously update the points on the weighted averages until you see that there's no change?
So
is that what you would have to do?
the
Or-
solution here is not to go iteratively. So it's like in a regression where we talked about the first time, here's the conditions that we need to have. And there was a closed form solution, right, the normal equations. In here, we take this equation and we say we're gonna minimize it, right?
Right.
And you saying, can I do this iteratively?
Well, what I'm saying is, could you make a copy of the network, right? And then from the original, take the average of the neighbors from the original, and then just update each one in the copy? Or do you have to take the original and then continuously update it until you don't see change? That's what I'm
Whether it's
confused.
a copy or not a copy, The problem is that initially I can't compute neighbors for everybody, right? I mean, there's a lot of things that are unlabeled. The only labels I have are 2, 8, 4, 9, so on and so forth. So there's no easy starting point to say compute the label here. Right? I think we have to look at the global space. The whole principle here with the heat equation says, can you look at the whole space and make some determinations based on the objective, which is this heat objective. Now, I think the question is pertinent, like, can I do it iteratively? If there is a greedy path forward that update this, done, then move to the next one, done, then move to the next one, done. I think that's possible in some cases, but not in general. It's hard to satisfy, I think, this equation here if you iterate 2 points and never go back. So I think there's 2 solutions once we figure this out. And one is iterative, but it requires like neural networks going back and re-update the points that you've already computed. You can't guarantee a straight path forward. So this theorem that says this is the solution we want, f has to have this form, is the one that guarantees locality. And then there is some mathematical condition like KKT that says, if you remember there, duality had to do with the eigenvectors. That's the same thing like here. There's an eigenvector type of equation that says the function is unique. It satisfies locality. That is this thing right here. But then this one saying it must satisfy this equation, aka t minus k times f equals 0, where k is the singularity function, t is the diagonal function. Now this is very related to something called Laplacian in graph theories. After this has been published in 2002, when Facebook came along with the graph theory, they looked at this from a graph perspective and what's called random walks. Like if I start from you and I go by your friends, where am I likely to end up? And there's a whole graph theory that has to do with this Laplacian of the graph, which is computed per point, has to do with the neighborhoods, neighbors of that point, which is pretty much equivalent to the heat theory. We won't deal with that. I'm just saying there's a totally different perspective of this problem, which is equivalent to the heat equation. And then there is, like in normal equations, a formula for how you can do this. So L here stands for labeled points, U stands for unlabeled points. And if you split this into matrices in this way, you could compute directly the F, which is the function you want, the temperature, for all unlabeled points by using a matrix equation. This is equivalent to the normal equation and regression function and closed form solution. But of course, this is impractical. So just like with the normal equations, if you remember all the way to the first week of the course, we said here's the solution, xt minus x minus 1. It's impractical. So even for linear regression, people still use an iterative method. Now back to your question. If I use an iterative method, it's still I have to go back and update points, just like regression, right? When we did gradient descent, we didn't set up a prediction for a point and then move on, never come back to that point. When you go to the second round and update all the regression coefficients, it changes all the predictions, right? Same thing will happen here. I can have an iteration that do this. So this is not an exercise, right? I don't have anything in the homework for this. This is not required for the exam. This is a way to say, I'm looking at a machine learning problem, either as a graph or as an equilibrium situation in which I can either apply the graph theory or apply the heat thermodynamics theory and then try to solve this equation, right? I mean, how do I minimize this exact function? It's up to me. The key here is that f will always be the average between the neighbors, which is what we want. The way we set up this problem from the very beginning was to say, whatever happens here, we want this to be the average of its neighbors. So that locality constraint makes this analogy with heat. Now in machine learning, we don't have to have that constraint if we don't want it, right? Like regression, a regression function doesn't have such a locality constraint. A regression classifier will never guarantee that a point has the same label as its neighbor or the average of its neighbors. it's very possible that two neighbors fall on different sides of the plane. But if we want a locality constraint, we have a different business than regression. Yes.
Would you happen to have like pseudocode or like a code snippet for the two?
I think this is a well-known thing. I don't have a pseudocode that I've run. I think some students in previous years tried to implement this for smaller. The problem here is like normal equation, the size of these matrices that need to be inverted. So if this is a big matrix, you know, can't take the inverse right away. So I think people have tried to do this even as a project in this class. You have to be, you have to pick the right data set and the right task to try it on, right? Like, in what classification problems do we need this locality constraint? So if I'm in a hospital and I talk about patients, does it make sense to do this? More than a global classifier. Versus if I'm in a real estate and I try to, you know, estimate the house prices. Does it make sense to do this? Well, I'm not sure. What's the distance between two houses? Like, what's the similarity between houses?
Future similarities, the area of house, the location of the house, their similarities.
Right. I don't know. I think real estate business has a lot to do with similarity, as in the same neighborhood. That's what they do when they check the validity, like trying to buy a house, what are comparable prices in the neighborhood. But then, from the point of view of somebody who's looking for a house, not in such a neighborhood, why is it that the house in this place has the same price as a house in the other side of the state, or just in a different state? That may not be a local problem anymore. So that's what I have for local classification here. Of course, this is not for the homework. You still have to implement kNN, and we have a perceptron. And we have one more lecture Thursday to do other things. I didn't decide yet what to do because we're kind of done here. But we could do, so things that are typically done in this class, but I didn't do them yet, are clustering. We didn't talk about clustering at all. We only talked about PCA, which is not quite clustering, but it's unsupervised learning. I don't plan to do clustering unless you guys want to, because there's so many other classes that do clustering. But there are those recommendation systems, for example, reinforcement learning, some more theory. Probably we'll skip the theory, so we'll have to decide what to do on Thursday. Yes.
We don't have class on Thursday. Last day of class is Wednesday.
The underground.
Oh, gotcha.
I see. So you guys can come if you want. Or you can stay home. We won't do anything related to the exams, okay? So everything I say on Thursday will not be, I'll try to not be, the problem with me sometimes is that if I start thinking very hard on exams, that happens in algorithms course. If I meet the students for any reason, I'm biased by the problems I have in my head for the exam. So, you know, whether it's office hours or class or whatever, I try to stay away from what's already decided to be in the exam. But yeah, we'll talk about fun things. Alrighty. So I'll be at office hours Wednesday and Thursday. Who's doing a project here? You guys have to talk to me. Okay. We're gonna need, if you do not waive a homework for the project, then there's no problem. But if you do waive one, we need a final, not report, I don't want a formal report, but task description, results, what happened. And in particular for a project, you have to explain why things don't work. So if any project has to start with the problem description, task, and immediately we want to see, here's why normal thing that somebody will try is not the right thing to do. Like if I try regression, right? Why is that not the right thing to do? Because for a project to be interesting, it can't be solved by a simple run-off-the-shelf algorithm and you're done. Right? So it has to be at least some bullets or paragraph in there to, okay, here's what people have tried, or I have tried, and here's why I think it's not working correctly. But it doesn't have to be a long thing, just we're gonna need something to grade by next week on the project. That is if you waive a homework.
That's fair.
Let me shut the camera.